Welcome back to Elementary Statistics. In this video, I want to talk about t-tests with dependent samples. I already talked about the general idea of a t-test on two sample hypotheses, and I already talked about the difference between independent and dependent samples. Really quickly, dependent samples are where we are comparing, for example, before and after data for individual elements of the population, individual members of the sample. And independent is where we have different groups that we are treating side by side and comparing at the end. And whenever we have dependent samples, we can construct a comparison distribution. Here is a very small distribution so that we can work on the calculations without spending forever in computation mode. I have 5 members of my sample of the population. I measured their score, let's say the size of a green bean, before and after we fertilized. So we have a plant with 5 green beans on it, which are measured at 4 centimeters, 6 centimeters, 7 centimeters, 5 centimeters, and 6 centimeters. We fertilize it. Afterwards, we have 5, 8, 8, 4, and 6 centimeters as their lengths. Our hypothesis, come over here somewhere. Our null hypothesis is that these are essentially the same. Our alternative hypothesis is that these are fundamentally different in some way. N is 5, that's N1 or N2. And when we are looking at paired data, instead of having to look at what is happening on average, we can take the difference beforehand. So we're going to introduce a new column here called capital D, which is just x1 minus x2, or you could use x2 minus x1. It doesn't matter as long as you are consistent. So 4 minus 5 is negative 1. 6 minus 8 is negative 2. 7 minus 8 is negative 1. 5 minus 4 is positive 1. 6 minus 6 is 0. This column D gives us a completely new distribution, and we can perform a one sample test on D. Our null hypothesis is that for the entire population, D is 0. Our alternative hypothesis is that for the entire population, D is not 0. We have that N is 5. We never chose a significance level. If nothing else, we always kind of default to 0.05. That's the standard in a lot of fields. But for these 5 data points, negative 1, negative 2, negative 1, positive 1, 0, we can find that if you add these together, you get negative 3, which means that the mean is negative 0.6, right? Negative 3 divided by 5 is negative 0.6. We can take D minus D bar, which is going to give me, all right, this is where things get a little bit ugly. Negative 1 minus negative 0.6 is negative 1 plus 0.6, which is negative 0.4. Then we get negative 1.4, we get negative 0.4 again, we get positive 1.6, and we get positive 0.6. We can square all of those things. Zero point 0.4 squared is 0.16. 1.4 squared is 1.96. 1.6 squared is 2.56, and 0.6 squared is 0.36. Add all of those together. And you get 5.2. And remembering the standard deviation formula, S is the square root of exactly this thing divided by n minus 1, which is 4 in this case. And when I punch that into my calculator, I get 1.14. If this was a larger set of data, the shortcut formula for calculating standard deviation also works here, but this is a small set of data, so this is perfectly fine as an option. Now our estimator, 0, is equal to d bar plus or minus our t-score times s over the square root of n. D bar is negative 0.6. Our t-score, we have to go to the table. We're looking at a two-tailed test with 0.05, and degrees of freedom is 4, which gives us that the t-score is 2.776. S is 1.14, N is 5. Punch everything after the plus or minus into my calculator. I get 1.42, looks like a good place to round it. And if I take negative 0.6 minus 1.42, I get negative 2.02. If I take negative 0.6 plus 1.42, I get positive 0.82. And 0 does in fact fall into this range. So we are going to accept the null hypothesis and we can conclude that this test did not provide any evidence of a difference between the samples. Right. Once more, since it's come up here, remember that accepting the null hypothesis is not saying that to within probability of 0.05, 5%, that they are the same. It's that we did find evidence that they are different. Right? If we reject the null hypothesis, then we did find evidence that they are different. If we did not reject the null hypothesis, if we accept the null hypothesis, then we did not find any evidence that they are different. That's all I have on this video. The calculations here are a little bit messier because you have to go through and do all of the calculations. We can't shortcut by having a known mean and standard deviation when we start, but that's okay. It's a nice chance to review those formulas. Thanks as always for joining me. I'll see you next time.